Can you see the screen?
No, sir.
Yeah, can you see my screen?
No, sir.
Yeah, not done. Oh yeah, maybe.
No.
I'm sorry, there is a problem with the internet. It's Wi-Fi, institute Wi-Fi. I don't know what happened. Anyway, I'm working with my phone network now. So, can you hear me? Can you hear me?
Yes, sir.
Okay. Can you see? Can you see
Yes,
my
sir.
screen? Okay. So, just 1 minute. So today we'll discuss the relation between integration and differentiation. Right. So this is what we'll discuss today. So suppose F belongs to RAB, which is this notation. RAB means set wall Riemann integrable functions on alright in a function G on AB was equal to introducing x t. Right, so this is a function of x. Elements. First thing is G continuous always. Similarly is G differential. Right. So what this function? This is very natural function. So suppose you have a graph of this x. It may have continuities. So for example here continuities as well. Suppose something like f is like that. A is this one and B is this one. And this one, so suppose pick a function, pick a point x, pick a point x, and you look at the data, and that so this is so this actually gives you integration a to x fx dx. So x can be not here, yes, x can be right here as well. This is this one, then the area would be so some of this, right? The whole thing, this whole thing, whole thing, x fx x.
Sir, your voice isn't coming properly. Like the internet is too bad.
Okay, right. So let me try to change the internet. We'll see whether either internet is back with full strength. Can you see my screen?
Yes, sir.
And can you hear properly now?
Yeah, it's better now.
Okay, that's good. Yeah, so we want to look at this function, which is actually the area from a to x under the curve f, if it is a curve. So geometrically, this function is an area function, and the question is whether g is continuous on a b, differentiable on a b, right? So now we'll prove actually that this function is continuous. So and right. So it is a theorem. Let f be a Riemann integrable function on AB and gx integration a to x fx dx. Then 1. G is continuous on AB. 2. If f is continuous at some point x naught in AB, then G will be differentiable. G is differentiable at that point at x naught, and g prime x naught is f of x naught, right? So that gives integration is kind of antiderivative. So if you look at this function, you look at derivative, you'll get the function. So it becomes it gives you a function whose derivative is f, right? Given a Riemann integrable function, if you can define this function, and if f is continuous, then this function is not just differentiable, the derivative, this function, so it is sometimes, right? So given a function, you want to know whether this is derivative of some function. That is important in some cases. I'll give you examples. um, so given a function, whether this can be seen as derivative of a function, how do you see it? So this is the way to see. You define a function like this, integration a to x fx dx, ft dt actually. So because x is the limit, yeah. Then this, if f is continuous, then you get the function g whose derivative will become f. Right. So this is the theorem. Is the statement clear? Right. You want to find, given a Riemann integrable function, you want to find a function whose derivative is that function. Right. So derivative function might not be continuous. Right. Derivative function satisfies certain properties but may not be continuous all the time. So f is just a Riemann integrable function, then can you see it as a derivative? In general, you may not able to see, but when f is continuous also, then you can see it. Continuous Riemann integrable functions, those you can see as derivative of some function. All right? Okay, so let's go into the proof of this theorem. So since f is Riemann integrable function, f is bounded. So that means there exists m greater than 0 such that mod fx is less or equal to m for all x in AB. So you get boundedness. Now, see, first thing we want to show the proof that if G is continuous, right? So pick let xy belongs to point in AB. And you can assume x greater than y. May not be needed, but yeah, let us see. Yeah, maybe we denote this by t because we are using t here and x as the limit. So right. So take 2 point x and y, and now you write gx minus gy, right? So gx minus gy is, this part is important. Either y greater than x or x greater than y, anything will hold. So without loss of generality, so this part without loss of generality, one can assume. So this is integration a to x ft dt, which gives you gx minus integration a to y ft dt. So that gives you, look at the properties which we mentioned few days back, that this function, this will be integration y to x ft dt. Right, so integration a to y, this will be negative of minus integration a to y would be integration y to a plus integration y to a, and then is one in the top and one in the bottom, so it will go. Anyway, this is the property of integration. So you have this one. Now you put modulus gx minus gy here, which is integration y to x ft dt, right? So this one is less or equal to integration y to x mod ft dt. So this is less or equal to m because f is bounded by m. So this one, we are using this term. So we get this is less or equal to m times integration y to x dt, which is m times x minus y. All right. Now, therefore, so given epsilon, choose delta to be epsilon by m, then we have mod of x minus y less than delta implies mod of gx minus gy less than epsilon, right? Which means actually not just continuous, it is uniformly continuous. So G is continuous. And continuous and compact set is uniformly continuous. So in any way, this would be uniformly continuous. Right? So look at, so is the proof clear? Yeah, what we did? We just used the definition of G and a property, how the sum, how it becomes the sum, something like this. Integration a to b fx dx is integration a to c fx dx plus integration c to b fx dx, right? Well, c belongs to the interval, c is a point in the interval ab, right? We are using this one. So is the proof clear? Yeah.
Yes, sir.
Right, so there is nothing much about the proof here. Let's look at now. So given f is continuous at x naught, to show g is differentiable at x naught. All right. Now, to show g is differentiable, you need to look at the quotient g x naught plus h minus g x naught by h, and then you calculate, right? So use continuity first. What is given? So given, since f is continuous, given epsilon greater than 0, there exists delta greater than 0 such that a mod of x minus x naught less than delta implies mod of fx minus fx naught less than epsilon. So you call it 1. Choose h greater than 0 without loss of generality such that mod h is less than delta. So actually, h greater than 0 is not needed. Choose h such that h mod h less than delta. Actually, no, greater than 0 is good. We'll see that analogously you can do it for less than 0. So g of x naught plus h minus g x naught, if you want to calculate, which is a2 x naught plus h fx ft dt minus a2 x naught ft dt. So this is x naught to x naught plus h ft dt, right? Now what we want to do is the following. We want to look at 1 over h, this by, so g x naught plus h minus g x naught by h. This is 1 over h integration x naught to x naught plus h ft dt. All right. Now what we want to do is we want to subtract fx naught both sides. X naught plus h minus gx naught by h minus f of x naught, which is, this is 1 over h integration x naught to x naught plus h ft dt minus f of x naught. Now this will be on the right hand side 1 over h integration x naught to x naught plus h minus 1 ft dt minus 1 over h integration x naught to x naught plus h ft dt. This should be 1 over h. This is not ft dt, right hand side, so this is just f of x naught. This is f of x naught because this is a constant, so integration dt, integration from x naught to x naught plus h is just h, so h get cancelled. So this is x naught to x naught plus h, f of t minus f of x naught dt. Right? Now you look at g of x naught plus h minus g of x naught by h minus f of x naught modulus. So this one is here less or equal to 1 over mod h integration x naught to x naught plus h mod of ft minus f of x naught dt. Now this is less than epsilon, right? So from 1 we have this is less than epsilon as t varies here. So this is less or equal to 1 over mod h times epsilon times x naught to x naught plus h dt. So this would be, since h is positive, so this will be 1 over h, since h is positive. This is 1 over h times epsilon times h. So this is epsilon. So what we get is, given epsilon, there exists delta greater than 0 such that mod h less than delta implies mod of gx naught plus h minus gx naught by h minus f of x naught is less than epsilon, right? So which means, in this is the definition of the limit as h tends to 0, gx naught plus h minus gx naught by h is equal to f of x naught, right? So this limit exists and which is equal to f of x naught. So is the proof clear? So what did we use? We just use the continuity of f here, and we used again this formula here as we mentioned, integration a to b fx dx. Integration a to b fx dx is integration a to c fx dx plus integration c to b fx dx. This one we are using here, and here we used the continuity of, here this one, the continuity of f will be used. Now then we are looking at the quotient. From the first principle we want to show the limit exists, and then here one small trick, f of x, one can write f of x naught as this one. All right. Now once you write this, you can get as an integrand as ft minus f of x naught, and t belongs to 0 to h, t belongs to x naught plus h. So that means the interval we are looking at is less than delta. Yeah, so where this part is satisfied. So one can use continuity here. One can use continuity here, and that is what we are using because mod h is less than delta. So continuity is being used here, and what you get is epsilon is less than epsilon. Yeah, so this part here one would become strict. So ultimately you get strict 1. Right, so you get strict epsilon. Yeah, is the proof clear? Yeah, is the proof clear? Proof is not very difficult, it's simple. Is there any question, or is it clear?
Yes, sir.
Yes, sir.
Yeah, all right. So now let us see a motivation. Why do you need such things? So it basically comes when you want to define the path integral. So for example, this is of course it is outside of our course here, but if you look at in a plane, so if you look at in a plane, 2 points, and for 2 points you have a lot of paths, right? You can go this way, you can go this way, you can go this way, this way. You can go this way. You can go this way. You can go this way. So there are several ways where you can go from one, let's say this point A to B, right? Now the point is, if you want to define the integration A to B, some function, suppose some function there, some function is there from here to R. So this is the some function, and you want to define this integration, right? Integration along the path, right? So the path integration you want to define. Well, if so, I mean, you may not be able to define this, right? Integration A to B. So you want to define integration A to B from this point to that point. But how do you define? There are several paths. So in general, you will not be able to define such integration. It actually, if gamma is this one, you want to define gamma. Integration f over gamma. So the integration, in general depends on the path. But sometimes it is important to know that some integration, it does not depend on the path. Whatever path you take, it should be, the integration will be the same. So sometimes the fact that the integration is independent of path plays certain important role, right? So sometimes we want to know whether this integration depends only on the endpoints, not the path how you go. Of course, this is a property of the domain which would actually which will actually say, so this is the property of a domain. If there is a, for example, if there is a hole inside here, if there is a small hole, then integration on that path, this path would be different from integration path this side. So it depends on how the domain looks like. So if there is no hole in R2, then perhaps then integration is independent of the path. That is actually, I mean, I think it is there in the syllabus of analysis 3. But what is important to know is whether the integration is independent of the path or not. And our next theorem gives very basic class of functions. Or maybe this next theorem will give the same thing in R only. So which means you have an interval. You have an interval, and you have function to R, and you look at integration a to b fx dx. So when this integration depends only on the endpoints, right? Only on the endpoints a and b, not inside. What happens? So yeah, so this is the fundamental theorem of calculus. Which is a basic phenomenon of much more general Stokes theorem in higher dimension. So this is a very important thing. This plays a very important role. It has a lot of generalizations, which generalization is called Stokes theorem, which you will know in perhaps some courses in analysis 3 perhaps, and some in differential geometry. But this is the basic stuff in R in an interval AB. Let's see what happens. So let f be a Riemann integrable function on AB. Suppose there exists a continuous function g from AB to R which is differentiable on open AB, and g prime x is equal to fx for all x in AB, open AB. Then integration a to b fx dx is gb minus ga. Right, you already know it from school. And we in school, when you want to integrate, you want to find a function g whose derivative is this function. And that's how you did the integration. That's how you actually evaluate the integration from school, right? So finding a function g whose derivative is f. That was the question even for, I mean, uh, indefinite integral or definite integral. The main point is to find a function g such that this holds. And once you have, then you just evaluate this one, right? This you know as a formula, right? From school. But let's see a proof now. Have you seen a proof in the first semester? Yeah. Have you seen a proof? Because it uses Riemann's definition only. So you must have seen a proof. Maybe it depends on whether there was time.
I think in the second semester we saw a proof. I think.
Okay, you saw a proof in the second semester. Yeah. So these things are in the second semester, yes. Yeah, so we have seen a proof. So do you want to see that again? Yeah, maybe briefly let me say it. So a sketch of the proof, not the whole proof. Tool, Riemann's definition. One is Riemann's definition. Of integration, and two is mean value theorem, right? So how do you use mean value theorem? Mean value theorem is used on G because given G is continuous on closed interval, differentiable on open interval, continuous on closed, continuous on closed and differentiable on open. So it is mean value theorem can be used. So on G. So by using mean value theorem, there exists Tj. So for Riemann's definition, we will consider a partition. X0 less than x1 less than xn equal to b. A partition. So where we'll use mean value theorem? On G on interval xj minus 1 xj. So there is point Tj in xj minus 1 to xj such that gxj minus gxj minus 1 equal to xj minus 1 f of tj. Right? Now what you do just summation both side gxj minus gxj minus 1, this sum over j equal to 1 to n, and this sum f of tj xj minus xj minus 1, j from 1 to n. Now you see here this part is automatically comes as gb minus ga, and this does not depend on, so this part does not depend on the partition. This part does not depend on the partition, right? So this becomes gb minus ga is equal to this one. Now here you increase the number of points and take the limit. So here increase the number of points in the partition, which means you are making refinements, and take the limit, right? As per the definition of Riemann, this gives you integration a to b fx dx by Riemann's definition. Right? You used tool 1 Riemann's definition here. that this side gives you Riemann integration, but this side gives you b minus a. That's the proof, right? So use this two tool, use mean value theorem and take summation on both sides. Yeah, is it clear? Yeah, you have seen the proof. So now you can recall this one. So this is nothing but using mean value theorem and then using the Riemann's definition of integrability. Any question here? Yeah, so next time we'll give proofs of, next time there will be three theorems. So one is integration by parts, then there will be change of variable, and there will be changing limit and integration. So changing limit and integration is very important one. Okay, and yeah, integration by parts and change of variable is also important. Okay. Yeah, so since time is almost up, so we'll just stop here. Yeah, any question?
Excuse me, sir.
Yeah,
Sir, could you please give some reference from where I can read about zero measure sets?
a zero measure set is there in Rudin's book in chapter 11. And well, there is measure theory is fully, he constructed what is Lebesgue measure. So in general, just zero measure set, looking at zero measure set would be difficult. So, but you can read a little bit of, what Lebesgue measure is on R. The properties, few properties that so do you have Rudin's book with you?
Yes, sir.
Yeah, so you can look at chapter 11 and see. So for Lebesgue measure, the length of the measure of the interval is the length of the interval. It's same. You want to generalize for general sets, and that's how you actually look at covers by intervals, and then look at the smallest covers which actually containing the intervals. So in looking at the infimum of the length, which covers that set. So that's how one get the concept of measure. And when this one is, one can make this sum of the total length is less than epsilon, then you say it is for every epsilon, then you say this is a measure zero set. So measure zero set appears in several contexts. You will see in measure theory, function analysis, and several other things. But just for measure zero set, I don't know a book. You can look at Sram's book whether this might have been given a little bit, not much. But Rudin books have a little bit of theory. So I suggest that you don't go into the full theory. Just look at the definition of what it is, and then go into the zero measure set. You can see few examples of zero measure set. That's it. You don't go beyond that. And actually, Rudin's in chapter 11, he also proves this Riemann integrability. The thing about Riemann integrability, what I have given in the notes. Okay.
Okay, sir.
Yeah. So I don't have any more references about zero measured set as such. But yeah, one can look at little bit of definition in Rudin. But In the summer, you can read that if you are going into mathematics. Okay. Any other question? Okay, then see you on Friday.